I want to talk about some normal distribution applications. So I've talked about what standard deviations are. I've talked about how to get a z-score. So now I'm going to look at a little bit of what can we do with z-scores? What else can be done? So two normal distribution applications here dealing with obviously z-scores. So the heights of males aged 15 to 18 years old is approximately normal with a mean of 70 inches and that should be and with a standard deviation of 2 inches. What percentage of males 15 to 18 are 73 inches tall or shorter? So some important things here are there is a mention of things being approximately normal. When things are approximately normal, that means you have that distribution, which is roughly symmetric and unimodal, and you can do z-scores. And then using z-scores, you could find proportions and percentages, things of that sort. So with this problem, since they said it's approximately normal and they're trying to find a percentage, what I'm going to do is I'm going to set up my normal distribution first and recognize that we do have a normal distribution with the center or the mean of 70 and a standard deviation of 2. Okay, mean of 70, standard deviation of 2. What we want to know is what percentage of males 15 to 18 are 73 inches or shorter. So if 70 is in the middle, 73 would be over here to the right as our cutoff point. That's what we're observing. And they want 73 inches or shorter, so they want to know what is this proportion or area to the left so that we could use it as a percentage. So what I'm going to do is I'm going to do a z-score, which we've talked about before, doing z-scores. I'm going to do my observed value minus my expected, and then subtract the standard deviation. Observed minus expected divided by the standard deviation. So 73 minus 70 is 3. 3 divided by 2 is 1.5. So what we can do is we can look up this z-score of 1.5 to figure out what is this proportion. So this is where that z-score table comes in. Okay, the z-score table always gives you the area to the left. So what I'm looking for is the z-score of 1.5. So I go in the left column, I look for 1.5. There it is. Across the top, if I want a second decimal point, like 1.51, 1.52, 1.53, I could use those, but it's 1.50, which is 0.9332. 0.9332. Okay, so why that's a little bit helpful for us is now I can wrote in my 0.9932. I can conclude my problem here. So a little bit of context. So I'm going to answer my question, which we're going to say 93, or sorry, I should probably say there is 93.32% chance a male 15 to 18 is 73 inches or shorter, or some sort of resemblance of that. Because they asked what percentage of males are 15 to 18 are 73 inches or shorter. Well, 93.32% of males 15 to 18 are 73 inches or shorter. One more thing I'm going to look up or do here is another application. If I want to be in the top 10% of heights for males aged 15 to 18 years, what is the cutoff height I need to be taller than? So again, from our introduction paragraph there, they did mention things were approximately normal. So I'm going to just start with a picture and label that information. So they told us the mean was 70, the standard deviation was 2. What's different in this second question is it says if I want to be in the top 10% of heights for males aged 15 to 18 years, what is the cutoff height I need to be taller than? Well, what they're telling you is if we're in the top 10%, that means we're over here somewhere. And they're telling us that this area should be 0.1000. What I don't know is I don't know what is this cutoff point. So this problem has a few layers here. We're kind of working backwards. It's almost like we're starting with a percentage and we want to work backwards and figure out what is this cutoff point? Is it 73? What is it? Okay. So what we're going to do is we are going to use a z-score table to try and figure out what z-score leaves you with an area of 0.1000 at the top. But the thing that you have to be careful about is the z-score table does not give you the area to the right. It gives you the area to the left. So if the area to the right is 0.1000, the area to the left is 0.9000. So what I'm doing, and let me make sure I pull up the right table here, is I'm going to look through my z-score table and look for the closest thing to 0.9000. 0.9000. The closest I'm going to get is if you look at a z-score of 1.2 and come all the way over here, here's 0.8997. So that's 0.0003 off of what I'm looking for. So this is going to leave me with 10% in the top and almost 90% on the bottom, and that's a z-score of 1.28. So if I'm going through my z-score business, which remember this is the formula for a z-score, I know this is a 1.28, and I know a few other pieces of information. I know my mean is 70, and I know my standard deviation is 2. Okay. So what we could do is we could use a little bit of algebra to solve this. Multiply by 2, multiply by 2. This is going to give me 2.56 equals x minus 70. Add the 70, add the 70, and that's 72.56 equals x. So some context there. To be in the top 10% of heights, you need to be, and I know I'm a little bit tight here, 72.56 inches or taller. 72.56 inches or taller. So that's just a little bit of working backwards. So this is just a few of the different applications you can see. It could be as straightforward finding a z-score, finding the area, reporting the area, or working backwards, starting with an area, work backwards through the z-score, and solve one of your missing pieces. Find the x, find the mean, find the standard deviation, whatever. Many, many different options. So that was a quick example on normal distribution applications.